Hello everybody, how are you doing? This is Professor Carlos Torres-Verdin broadcasting live from the beautiful hill country of Texas. Look at this incredible, majestic, gorgeous, native Texas wildflowers. The bees are having a feast with the colors, with the sugar, with the pollen, everything. And we are also going to have a feast of a lecture with Principles of Formation Evaluation, PGE358, Spring 2020. Today we are going to talk about spectral gamma ray logs. We are going to show cases where the standard gamma ray log does not work to assess volumetric concentration of shale. Examples of that taken from the Compendium. And then we're going to show how spectral gamma ray logs, which separately measure the natural radioactivity of potassium, thorium, and uranium, can be used to once again properly assess volumetric concentration of shale. And then we are going to show that additionally spectral gamma ray logs can be used to assess the dominant clay minerals included in a shale, in a rock. And with that, we're going to show another set of examples. The entire lecture has been designed to be in PowerPoint mode, so everything is going to be self-contained. It's going to be a very practical lecture, and we will have tons of fun, just like these bees. So, fasten your seatbelts, enjoy the scenery, and let's go for the lecture now. Hello everybody, welcome again to an exciting, interesting lecture. Today we are going to talk about spectral gamma ray logs. Let me just say, the objectives are, first of all, to explain why gamma ray measurements are used to diagnose, quantify the presence of clay and shale, the mechanics of the physics behind the measurements. Then we will introduce the spectral gamma ray logs, which are separately acquired for the spontaneous gamma ray activity of potassium, thorium, and uranium. Then we will use some time to describe the measurement principles, the calibration, and the environmental corrections of gamma ray logs. And then we will give some examples of abnormal gamma ray measurements where the gamma ray log doesn't necessarily correlate well with volumetric concentration of shale. That will be an important message out of this lecture. Then, to complete the process, we will explain how to use spectral gamma ray logs to diagnose dominant clay mineral composition of rocks. The material that goes with this lecture is comprised in the PowerPoint presentations that are listed here. I'm also going to use a few pages of PGE358 well log compendium. The pages are listed there. It will be well logs and outcrops. And then I'm going to use at the very end a Schlumberger interpretation chart, the so-called lithology-2 chart, to identify dominant clay minerals present in shales. And this lecture is complemented by chapters 6, 8, and 9 of the textbook. Have you looked at the textbook? Please do. Spent a lot of time writing that textbook. It's not complete, but it has a lot of very useful information. All right, so here we have seen a photograph of shales. We have seen many of them for quite some time, but here we have one that goes for fluvial systems. Now we know where the shales are. Now we know where the sandstones are. Now we know what types of shales we have here, and we also know that we might have some clay minerals in the sandstones. So the question is, why is the gamma ray log so widely used to recognize shales or shaliness? How does it work? What is the physics behind the measurement? Different outcrops, different structure of clays, different geometrical properties of shale layers. We have lots of variability in space and thicknesses and so forth, so on. Yet the gamma ray log is often very good at diagnosing and assessing and telling us about the presence of shales. We have also looked at cases where we have pure shales, and those pure shales can vary greatly in composition, facility, and other important properties. We also talked about the difference between shale and mudrocks, and we also talked about the definition of the pure shale. And there are, of course, also organic shales like the Eagle Ford shale shown here, where also the dominant grain composition is calcite. Shale comes in many multiple ways, and it comes in many multiple geometries in which it places itself in the rock. And that is all determined by the genesis, by the sedimentary environment, and by the diagenesis, the subsequent alteration, chemical, mechanical, that the rocks suffer, burial, high pressure, high temperature, etc., etc., etc. So we have what we see in rocks is the ultimate result of the genesis and diagenesis. And because of that, some of the shells, some of the clays are going to be mixing when the rock is formed, but some of the clays are going to be formed as a consequence of the burial process. So, some facts about shales and their natural radioactivity. We know that shales and clays are naturally radioactive. So that means that they release gamma rays spontaneously. We don't have anything to do. We don't have to excite those gamma rays. They're emanated in a spontaneous way. What are those? Mostly those are comprised of potassium, thorium, and uranium. Which are, and why do we focus on those three? Because the three are rock-forming elements, chemical elements. They are radioactive, and most importantly, their half-life, the time it takes for a certain amount of concentration volume to go to 1/2, that half-life, because of spontaneous release, spontaneous decay of radioactive material, that half-life is comparable to the age of the Earth. And because of that, we can take those measurements as a benchmark. The gamma rays emanating from those three elements, we can take them as a benchmark because their concentration, their volume, will be approximately the same for all practical purposes through the history of the Earth. And in addition, we know that there are many clay minerals that contain potassium, for instance, the elite clay group. So potassium is a very common chemical element that comes in the composition of clay minerals. The other thing we know is that uranium is often present in shales in the form of soluble organic material. Similar with thorium, we know that it exists in shales in the form of non-soluble absorbed impurities and also in the form of detrital material. Now, those are the three radioactive elements that we're going to focus on for the production of the gamma ray log. And those are the three radioactive elements for which the system that acquires the gamma ray logs has been designed. But there are some issues and there are some problems. There are some rocks which have no clay or shale or have negligible clay or shale, but they do exhibit abnormally high concentrations of thorium, uranium, and or potassium. And because of that, sometimes we can have high values of gamma ray log, and guess what? That will not be shale. So how do we know that that's the case? Again, the Earth is very diverse. We always have variability, and there are cases that go beyond the rule. So we're going to look at those cases. And the other thing to take into account is that sometimes the drilling mud itself can have presence of potassium. And because of that, some of the measurements could be affected by that potassium and will not be reflecting the concentration of potassium in the rocks. Now, how are gamma rays measured? Well, gamma rays are photons. It's a photon, no mass, no charge, no electric charge, it's just energy. But gamma rays have a spectrum of energies. Their energy is proportional to their frequency. And the constant that ties frequency with energy is Planck's constant. Now, every single radioactive element emanates gamma rays with different energies. It's almost like they have their own code, their own peaks, their own dominant values of energy that they send photons with. Every single radioactive element has a very well-defined spectrum of gamma rays of photons. So how do we detect them when they come from the potassium, the uranium, and thorium that we have in the formation? To do that, we have a system that uses, first of all, a scintillator. A scintillator is a system, a device that has a photon, a gamma ray coming into it, impinges upon it. It's a scintillating crystal, in this case mostly sodium iodide, and that impact converts the photon into light, and the light goes into a system of meters that amplifies the original intensity of that light beam. It's a system of multiple amplifications so that the initial signal coming from the photon is multiplied, and therefore it's easier to detect and to measure. These systems, what they do is they count the number of photons per unit time that reaches them. They're spontaneously released by the formation. If you look at this from a statistical viewpoint, the probability that the formation releases a photon, it follows a so-called Poisson distribution. And the other thing that is important to take into account here is the size of the gamma ray crystal. That size of the crystal, so that you know here, is about, it can vary between half a foot and a foot, or sometimes shorter. But the reason why it has that size is because we have to help the system to welcome, if you will, as many gamma rays as possible given their probability distribution that they come. So the larger the crystal is, the higher the probability that more gamma rays will impinge upon it. So that's the point. And then the other thing that we have to take into account is that this system is moving because the tool is moving at the same time that we are recording the measurements. So the counting that we do of gamma rays of photons has to be per unit time. So we call it a count rate. So that's how how the system works. Of course, these scintillators are very, very sensitive to temperature. So corrections have to be made because of the presence of the temperature. There are other corrections that need to be implemented that I'm going to talk about later. Now, if you look at the energy spectrum of gamma rays, energy in kilo electron volts, is in the x-axis. You will find that uranium, thorium, and potassium, they have their gamma rays emanating at different energies, that is to say, at different frequencies. Some of them have a central peak like potassium, but some of them, like uranium and thorium, they have multiple peaks. Thorium is related to the peak of thallium because that's the first subproduct of the decay, radioactive decay, whereas uranium is associated with bismuth, and potassium with potassium, and thorium and uranium at the very low energies, they also have peaks, common peaks associated with thallium and bismuth. So what the logging companies do is that they design the scintillators to have windows that cover the peaks of energy associated with the thorium, the uranium, the potassium, and the uranium plus thorium. They might have several energy windows and sensors that collectively open the gates and they count how many photons impinge upon the scintillator as a function of time, the count rate. And of course, the scintillator itself, the sodium iodine, has its own sensitivity. It tends to blur some of the peaks, but that's also taken into account when we make the measurement. So what happens with the standard gamma ray logging tool is that the logging companies design these sensors to open all the gates at the same time, all the windows of energy at the same time, so they welcome, so to speak, the photons that are coming from potassium, from thorium, and uranium, and they do a linear combination of the count rates. In that linear combination, the numbers that are applied to each one of those count rates is a function of the tool. And additionally, those count rates, they need to be calibrated with some standard that I'm going to talk about in a second. So essentially, standard gamma ray log is a weighted average of the count rates coming from potassium, thorium, and uranium. The calibration facility, there are many. Some of those calibration facilities are at the University of Houston. Some of them are with the logging companies. And here we have a plot of one such calibration facility where the tool is made to run on across boreholes of a certain size, filled with a certain mud, and they go through blocks of artificial material, which we know what their composition is. So what we want from this is to make sure that when we convert the count rates into gamma ray American Petroleum Institute standard, that conversion is properly calibrated. So regardless of where you go in the world, you will have the same count rates calibrated so that they are not affected by the location, by the size of the tool, by the particular electronics of the tool, by the scintillator. All of those conditions, they need to be calibrated so that regardless of the logging company that you use, you will get exactly the same measurements. In addition to that, all these logging tools, they need to be calibrated in the field. So there's another calibration device that is run on site just to make sure that the system is properly calibrating. And last but not least, these measurements, gamma ray measurements, are sensitive to a number of things, most importantly temperature and some of the borehole environmental conditions such as borehole size and the mud composition. Specifically in the mud, the presence of barite, because barite is heavy, and so when gamma rays try to make it through the borehole toward the scintillator that we have in the tool, if the material that you have in the borehole is very dense, then what's going to happen is that many gamma rays are going to be absorbed by the mud before they make it to the tool, and because of that, the count rate will be abnormally low, not because the rock is or has negligible concentrations of potassium, thorium, and uranium, but because many of the gamma rays that came from the tool were absorbed in the mud. So those are the things that we have to do. The other thing that's very important to understand is that the gamma ray log for most applications has a resolution of about 30 centimeters. So I was showing you the distance that we have here is about this distance over here. But if you want a better measure, somewhere around the size of this ruler over here. That's the resolution. So when it's moving, we cannot detect super thin layers or layers that are thinner than this size. The second point that is very important to remember is that when the formation is sending gamma rays spontaneously, there's a point at which the gamma rays originating from far away from the borehole will not make it to the borehole itself because they will be absorbed by the medium. So because of this, the measurements have a natural depth of investigation which varies according to whether the formation is dense or light. The denser formation has more absorption of gamma rays than a light formation, so we also have to take that into consideration. But we're looking into about, let's say, give and take 60 centimeters. That distance will be much lower if the formation is very dense. Those are the things that we have to take into account when we analyze and interpret gamma ray logs, especially in the context of other measurements. So the question is, why are shales or clay minerals naturally radioactive? That's the key point. And the answer is, we have to look at how these rocks are made. So when rocks are made, so to speak, in the rock factory, they come as igneous rocks. This is a beautiful picture how my cousin gave this picture to me for free, for enjoyment, and now I'm using it for my lectures. So enjoy it. Isn't it beautiful? And this is how rock is made, coming from magma. So when it comes on the surface of the earth, it has a multitude of chemical elements in its composition. Let me show you what that means. Over here on the y-axis, I'm showing the abundance of a given chemical element that is present on a typical rock that is formed in the crust of the earth. And on the x-axis, we have the atomic number. So the elements become heavier and heavier as we move farther and farther away into the x-axis. But, so the elements that are the most abundant, those are the ones that are shown here in this ellipse. And those are the minerals that, by the way, are those are the chemical elements, that are present in most of the minerals in the Earth's crust. You can see oxygen, aluminum, silicon, potassium, calcium, iron, so forth, so on. The important thing about these elements is the following. Not all of them are naturally radioactive. Some of them are naturally radioactive. And even if they are naturally radioactive, not all of them have the same half-life. Of all of the ones that we have here, we have radioactive elements. They have very long life, but half-life is potassium, thorium, and uranium. So I'm showing them here at the very end of the spectrum. So what happens is this. So if a piece of rock is coming from the earth, freshly made, right here, and then if you take a sample of all the chemical elements that you have, then that sample, that spectrum will be like I showed before. But not all of them will be radioactive. So what happens if you take that piece of rock as it shows to the surface, and now it's subject to weathering, be it in mechanical weathering, mechanical form, or in chemical form. So what's going to happen is that process will be a very long process. What will happen is that the rock will be ground to smaller sizes, and then also we will immediately see that clay minerals will show up. Clay minerals do not originate when the rock is made. They do not come in the rock factory, so from the rock factory. Clay minerals happen because of alterations. The rock is no longer at stable conditions at the surface, it's no longer stable in its crystalline structure, solid composition. When you modify the temperature, the humidity, the pressure, and because of that, they tend to stabilize by producing minerals that are more stable under the new conditions, and those are clay minerals. So what happens is that over time the rock becomes smaller and smaller, is being ground, and also we have the formation of clay minerals. And when that happens, which is a very long, arduous process, millions and millions of years, then what happens is that only the radioactive elements whose half-life is very long will continue to emit gamma rays from the same or almost the same initial volume. So they can be used as benchmark, and that's the reason why thorium, uranium, and potassium are so attractive to be used as benchmark. Their half-life is very close or longer than the age of the Earth. And also, they are commonly present in rocks when they come to the surface of the Earth. That's the reason. So here we have a diagram. The rock factory is at the very top, and then rocks are being ground, and they're also being altered chemically and mechanically. Clays begin to be formed, the fragments begin to decrease in size, and consequently we come all the way to the sedimentary cycle, and we have dominance of small particles with lots of clay minerals. And because clay minerals are highly present, because potassium is highly present in clay minerals, then we have abundance of those elements. Similarly, if the sedimentary process mixes organic material, which is soluble, then organic material will tend to have significantly higher non-negligible amounts of uranium, and that will come over with the composition. So if you take a rock sample when you have it on the surface, it will have, of course, immediately off the rock factory, it will have presence of potassium, uranium, and thorium. But their concentration, their volumetric concentration, will not be nearly as high as when the rock has been subject to this weathering, mechanical and chemical weathering cycle, where clays have been formed and where organic material has been mixed. All of that will collectively work toward concentrating the chemical elements potassium, thorium, and uranium. And as a consequence, because of their concentration, their natural radioactivity will also increase. That's the principle, and that's the reason why shales have their count rates for uranium, thorium, and potassium is considerably larger than clean sandstones or even rocks that are freshly made off the factory. Of course, there's also the possibility that when you make the rocks in the rock factory, you can grind them immediately. And when you grind them immediately and you bury them immediately, then the only types of clays that you're going to have are those clays that are formed after you bury them in the form of orthogenic clay, like chlorite, for instance. But if the rock is subject to this prolonged period of millions of years of the cycle of weathering and erosion to decrease the sizes, accumulate organic matter, and also accumulate clays, then the process will give rise to a different concentration of thorium, uranium, and potassium. And we'll talk more about that. So when you have a transport system, as I said before, that is grinding the rock, is increasing the rock fragments, the size of the rock fragments, is rounding them, and also is accumulating organic material, and is also accumulating clays. So at the very end of the process, we will have a high concentration of them, and because of that, the volumetric concentration of thorium, uranium, and potassium will increase, and because of that, the gamma ray count rates will increase. This is just to indicate how the process goes, and as a consequence, if we log the gamma ray log in any of these wells, we are going to see that the count rates typical of the gamma ray log will be indicative of the volumetric concentration of thorium, uranium, and potassium, and that's the reason why those concentrations can be related to the presence, not presence of shale. Interestingly, isn't it? And I have shown this outcrop because I like it. I think it's very textbook example. So once again, look at the layers of shale. Please note that the weathering cycle that they have been subject to is much more pronounced. They have clay minerals, which we don't have in the sandstones, and when they are made, where we're mixing them in space, and that's the reason why they come out to be in this outcrop what they come out to be. But bottom line is what we're looking at, the radioactivity, which is the radioactivity of potassium, thorium, and uranium. That radioactivity is the one that is going to be manifested in the gamma ray log. And as I said, clays, many of the clay types, chlorite, illite, they have in their structure potassium. So many of these clay minerals that are formed in groups because alterations of the rock, because clay minerals, as I said, are the byproduct of the alterations, they will incorporate potassium in their crystalline structure, and because of that, potassium tends to be the one that originates a heavy amount of the count rates, radioactive count rates originating or measured with the gamma ray logging tool. So when we look at the fractions of shale and fractions of sandstone, we know that both of them are going to have concentrations of potassium, thorium, and uranium. We know that. But the most important thing to know is because of the origin of the two, we will tend to have higher concentrations of thorium, uranium, and potassium in the shales than we have in the sandstones. And that's the reason why the gamma ray log in shales naturally will exhibit larger values than in sandstones. Now, if you look at the gamma ray counts, API units, American Petroleum Institute calibrated units, we're going to see that there are certain minerals such as quartz, dolomite, and calcite that have negligible, zero potassium, thorium, and uranium, and consequently their gamma ray logs are going to be small. But look at other compositions of grains such as feldspars, groups like mineral groups such as orthoclase and orthoclase, microcline. All of those have abundant potassium concentration, not in the clays, but the way the rocks were made by Mother Earth, the magma composition, their origin, will come with lots of potassium, and because of that, the values of gamma rays that they will exhibit will be very high. This is going to bring about some problems when we try to look at the gamma ray logs in sandstones whose grains are made of feldspars, because we will see that those so-called Arcos sandstones will exhibit very large values of gamma ray log that if we don't pay attention, they could be mistook for those of a shale. Similarly, for mica and muscovite and biotite, we have relatively high concentrations of potassium, and because of that, the gamma ray log through them will be relatively high, 270 GAPIs. For other minerals or other rocks, shale in this case, the variability is extremely large because of the composition. Kaolinite also doesn't come in one form. It has variability, same with chlorite, elite, mormorillonite, which is also called smectite, and other minerals that are formed in evaporites such as sylvite and carnallite. We can have very high concentrations of potassium, and consequently the values of gamma ray can be very high. So the question is, are there any cases where the gamma ray log will not be reliable to quantify volumetric concentration of shale? Are there any cases? And that's actually a very important, very interesting question. Let me show you an example of this situation. This example is taken from page 94 of the well log compendium part 1. And what happens here is very interesting. Let's look at the spontaneous potential log. We have the caliper, we have the gamma ray log, then we have the resistivity logs with different depths of investigation, where the deepest sensing resistivity log is the one color in red. Then here we have the neutron and density logs expressed in sandstone porosity units. We have also other logs here that I'm not going to talk about, but here in this track we have the compressional and shear sonic logs. But what I want to point out is this. If you look at the values of gamma ray log, first of all, it appears that the values are extremely high, except in some portions here that look like shale. But why are the gamma ray logs so values in cases where we have rocks that are invaded? The rocks are permeable. Look at the density log, is indicating that we have good porosity. In other places we don't, but in most places we do. And in fact, the density log correlates extremely well with the separation of resistivity logs that indicate invasion. Let's go to the right. I did a zoom of that plot on the right. Again, gamma ray log, spontaneous potential, resistivity logs, deep sensing log is the red. And here is the density log. So what I was trying to say is that it appears that this area over here is a permeable, porous and permeable rock. Same over here and same over here, because we have signs of invasion and because the density log tells us that we have good porosity. Yet, look at the gamma ray log over here. It's indicating very high values of gamma ray log. In fact, we do have a shale that takes place over here, and the gamma ray log values for that shale are actually smaller than the values of gamma ray for the sandstones. So what happens here? What happened? So what happened is that the gamma ray log is not reliable to assess volumetric concentration of shale. It just doesn't work for that. And why is that? Well, it turns out that these rocks have abnormal grain composition. The grains that make up these sandstones have abnormally high concentrations of potassium. So the potassium itself is not coming from the shale, it's coming from the grain composition. But we can understand that there's a problem because we're looking at all the logs, and the presence of invasion and the presence of high porosity, the presence of permeability just doesn't make sense in the context of a high value of gamma ray log, which for these values, it will be more like the value of a shale. And you can actually see that the values here, if you look at the scale, they're very close to 200 GAPIs. So here's an example where things do not work for the gamma ray log. And why? Well, what happens is, like in this rock that I'm showing you here, is that when you magnify the grain pack, when you look inside the grain pack, you are going to see that the grains that make up that rock, they do not have uniform composition. And in fact, when you do mineral analysis of the grains, you realize that these grains have abnormally high values of potassium, either because they came from a previous shale, that would be the structural shale, or because they were made from a rock that from the beginning, when it was made by Mother Earth, it had abundant concentration of potassium. And it was ground very fast, and it was buried very fast, so that the potassium in the grains was not decomposing to clays. The grains were ground and packed in place, and they were buried. So this is a typical history of of what is called a narcos sand. Another possibility, which I'm going to talk about later, is when the sandstones are interspersed, or they have some presence of volcanic material in the form of volcanic ash or tuffs, ignibrites, elements that come from the presence of eruptions, volcanic material that is deposited at the same time the sandstones are being formed by natural processes. So when we look at sandstones, please note that sandstones do not have necessarily the same grain composition across the planet. Some of them are siliciclastic, like the one shown here, but some of them are made of calcareous material. They don't have any abnormally high concentration of potassium, but when you look at these types of grains, this picture I took in Iceland, all of these grains are made from volcanic material. So they haven't really experienced a whole geological cycle of weathering. So if you magnify the grains, you will not see clay minerals. Maybe a few zeolites, but not a whole lot of other clays, especially not clays with abundant potassium. So as a consequence, because they're freshly made and because their composition has abundant potassium, if you measure the gamma ray log of this, the gamma ray log will tend to give you very high values. And then if you are naive, you haven't taken this class, you haven't analyzed, you don't know how to combine all the logs, then you will say, I'm just looking at the gamma ray log, and the gamma ray log is telling me that this is a shale. But it is not, because you have to look at all the logs, just not one, and whatever evidence you come across, and you conclude it has to honor all the logs. And as I showed you in the previous example, well, it doesn't make sense to have a porous and permeable rock and at the same time have high values of gamma ray. Or as an example on this rock at the lower left corner, where the composition includes high concentration of shale in the grains, and naturally the gamma ray values will be very high, but still the rock is permeable, it has good porosity, and it has good permeability. Another example that I often use to show this is an outcrop in San Jorge Basin in Argentina, in the south of Argentina. This is a place where I used to work for about 2 years when I was working with YPF. And the sandstones there were extremely complex and difficult because when they were made by Mother Earth, most of them were fluvial kind, but at the same time there were all these eruptions of volcanic material taking place because of the formation of the Andes, and there were blankets of volcanic ash, tough material, and all of those were interspersed in the sequence. So when you look at the sedimentary sequence, you have grain packs of grains that are not that were subject to a common or a standard weathering cycle, grain packs, but at the same time you will see fragments or layers of volcanic ash or tuff. And what happens is that because the age of these materials, the tuff they're very young with respect to the age of the other elements of the sedimentary sequence, and because they're loaded with potassium, then you run the gamma ray log here, and what happens is that you're going to see low values of gamma ray log in the sandstones. If the sandstone has an intralayer of volcanic ash, then immediately the gamma ray log will increase in that sandstone. And of course, when the gamma ray log goes across a tough unit like this or an ignimbrite, then the values will tend to be high. And again, you cannot say that this is a shale if you're naive, if you have not taken this class. You have to look at all the different logs in order to be able to assess that they might be a problem with the composition of these units that causes the gamma ray log to exhibit abnormally high values that could be confused with those of a shale. And here is an outcrop photograph again in San Jorge Basin, where you can see the abundant deposition of tuffs. And if you run the gamma ray log through here, and if you compare the gamma ray log values to those of a sandstone, you will see that tuffs will have much higher values of gamma ray log than the shales, even the shales. And also with respect to the sandstones. And the reason why is that all of these tuffs have abundant minerals with potassium. That's the way they were made by Mother Earth. Another very interesting example that comes from the Compendium is on page 33. We have looked at this before. It's a set of logs from the North Sea. Very interesting example where we had a shale at the top, and then we had presence of gas, then oil, and then water, and we had this beautiful capillary transition. But today, what I want to talk about is about the gamma ray log of this unit. And I did mention something about the gamma ray log during class, but if you look at the gamma ray log at the top portion of this figure, over here, higher than 8,500 feet measured depth, what we see is that the gamma ray log values begin to increase. And you would say, well, they begin to increase because the shale concentration begins to increase. Let's go to the right and show you what happens here. So this is on the right one is an enlarged view what I was just talking about. What happens again, the gamma ray log values begin to increase. And you say, well, it's a shale, or it's becoming shaly. But look, we continue to have very high, very large separation between neutron and dense logs. The resistivity logs continue to be high despite the fact that the gamma ray log increases. So what's going on here? It just doesn't make any sense, because if this were a shale related effect, what we will see is that the crossover between neutron and dense logs will begin to decrease. And second, the resistivities will begin to decrease. They do begin to decrease at about 8,320. That appears to be already the presence of the shale. But between 8,320 and 8,500, that increase of gamma ray log values does not correlate with what we see in the other logs. And what's going on here? So it turns out that this segment of the sedimentary sequence in this well in the North Sea begins to have abundant concentration of volcanic material. And so the volcanic material was, I don't know the history, the geological history of that region of the world, but what happened is that there were pulses of volcanic activity here that contaminated, so to speak, with volcanic ash some of these rocks, and as a consequence, the gamma ray log began to have high values. So obviously, the gamma ray log in this segment of the well is not representative of volumetric concentration of shale, and if we wanted to use the gamma ray log to quantify volumetric concentration of shale, then we will have to correct for this drift, if you will. So that's another interesting example. Yet another more interesting example takes place in Texas in the Vicksburg Formation. Let's look at this example. This example is on pages 47 to 49 of the well log compendium. Here we have the gamma ray log, then we have the resistivity logs, the deep sensing in red, the shallower sensing in green, and then we have the density and neutron porosity logs expressed in Sandstone porosity units, where the density log is colored in red and the neutron log is colored in blue. What I want to show you here in this is the Vicksburg Formation, something really interesting. What we see here is that in many parts of the log we have a mirror image between the gamma ray log and the resistivity log, many parts. And that's the reason why I'm plotting this in the way I'm plotting it. But in some sections, that mirror image doesn't happen. It's actually a copy image, such as in this area. And what's going on there? Look at the density log. The density log is indicating that most of these places where the resistivity log increases, we have an increase in porosity. The rock becomes lighter. That's actually very nice. So those are the sandstone developments. These are shaly sandstone developments. And we have a tendency to have crossover between neutron and density. All of these layers, this formation produces dry gas. All of these. There's absolutely no water here. It's all dry gas when they produce. And but the interesting thing is that if you just look at the gamma ray log here, you would say, those places where the gamma ray log are high, they necessarily have to be shales, because that's what I learned. Okay, so if they're shales, why is it that the resistivity log increases as opposed to decrease? And second, why is it that the density log shows increased porosity? So it doesn't make sense. And this situation doesn't happen everywhere. Some places it works very well. Look at this. Mirror image between the gamma ray log and the resistivity logs. Increased porosity as indicated by the density log. Let me do an enlargement of this section over here. When you do the enlargement, what you see here is what I was just mentioning. Increase of values of gamma ray log, of resistivity log, but increased values of gamma ray log. And then we have an increased porosity because the density log is pointing to the left. So this appears, if you just look at the density log and the resistivity log, you say, well, that's a sandstone development. It's not a clean sandstone development, but it's a sandstone development. And the tendency is for the neutron and density logs to overlap, so you might have light hydrocarbons. And the resistivity log also indicates that tendency because of Archie's equation. But gamma ray log increases, so the gamma ray log insists that this be a shale, but it's not. However, if you go to the second development here, everything works fine because you have an increase of porosity, you have an increase of resistivity, and you have a decrease of gamma ray. But not here. What's going on? Similarly with what happens at the bottom here. We have, in this area, we have high resistivity, low values of gamma ray, mirror image between the two logs, and we have an increase of porosity. But if you go to the lower one at 1800, yet we see a slight increase of porosity, a slight increase in resistivity, but a significant increase of gamma ray log. So what's going on? What happens here is also very interesting, that we have over certain bands and sections, we have presence of volcanic material, which has abundant concentration of potassium, which was mixing in when the sandstones, the grain packs, were being formed. So because of that, the grain composition has abnormal, or the matrix composition, better said, has abnormal concentration of potassium, but I want to insist that that only happens in certain sandstone. So it's almost like these pulses of volcanic material were not constant, they were intermittent pulses. Beautiful example. Now, what happens is this: when you look at igneous rocks, intrusive igneous rocks, and you drill the well and you measure the gamma ray log, you're going to, of course, have high values of gamma ray log in the shales, low values of gamma rays in the sandstones. But when you cross this intrusive igneous material, the gamma ray logs are going to increase in value. Why? Because this igneous material is loaded with potassium coming from the rock factory, and the potassium hasn't been disgregated, ground into tiny particles. It hasn't been subject to the same weathering mechanical and chemical cycle as the other rocks, and because of that we are bound to have abnormally high differences in the concentration of some elements. So bottom line is that the gamma ray log through the intrusive rock here will show relatively high values of gamma ray. Now, another example that often happens is the presence of rocks called evaporites. Evaporites like gypsum, halite, carnallite, for instance, they tend to have abnormally high concentrations of potassium. So when we have those, for instance, in carbonate rocks, we are going to see that the gamma ray log tends to increase in them because of the abnormally high concentration of potassium. But again, we have to not confuse them with gamma ray logs. Once again, when you look at these things and the gamma ray log is showing you excessively large values, there's a way to know that you have a problem, because if you look at the other logs don't make any sense with the high values of gamma ray logs. Like for instance, high porosity and permeability indirectly indicated by the presence of mud filtrate invasion, and then high values of gamma ray log. Well, it doesn't make sense, you see. So when you look at all the logs together, holistically, so to speak, then there's a way to detect that there are problems. And those problems usually happen because the matrix, the grain composition, is abnormally loaded with either thorium, uranium, or potassium. When you do the gamma ray log across shales, across carbonates, like this is a beautiful outcrop of the Edwards group just here in Austin. And I'm going to show you some more pictures of this when we go through the presentation of carbonates. But what we see in carbonates is that if you run the gamma ray log here, the gamma ray log will be 0 and absolutely flat. It's almost like somebody stopped the operation of the gamma ray log. It's dead. And that's because many of these carbonates have 0, negligible presence of potassium, uranium, or thorium. And so when you run the gamma ray log through here, it tends to have almost 0 values and very flat values. Whereas if you look at the density log, you will see that some of these formations will have porosity. If you look at the resistivity logs, some of them will have very low values of resistivity when the porosity is interconnected, and very high values of resistivity when the rock is solid like this. So that's another thing that we have to take into account when we look at gamma ray logs in carbonates. But there are certain types of carbonates that are very, relatively deep at the bottom of the sea that are formed, where they might mix with turbidite systems. So what we see here is a beautiful outcrop. This one is from Mexico. We have some chert right here, but we also have intralayers of shale, and then layers of carbonate. So if you run the gamma ray log here, you will see it will be almost 0 through the carbonates, and then it will have a spike increase through the shales, and so forth, so on. And those spikes are because these shales happen to be mixed in with the carbonates because of turbidite systems. So the turbidite systems dump all the sediment, and the sediment the water, when they go into the water, water is very effective at separating particle sizes, and it creates these very long, elongated distal lobes of the turbidite system that, because of the genesis of carbonates, they have cycles of sedimentation. Bottom line, we have to take those into account when we look at the gamma ray log. Now, how do we fix the problem of having high values of gamma ray log and not being a shale? The answer is to use spectral gamma ray logs. How do they work? Spectral gamma ray logs is actually a tool that has 3 separate scintillators and photo-multipliers. It's not the same. In standard gamma ray logging tool, you have only one scintillator and one photo-multiplier that opens the energy gates for all the photons coming from thorium, uranium, and potassium. The new tool, spectral gamma ray log, is separated with three scintillators, and each one of them is tuned to have a particular window. And the window is going to capture gamma rays for that particular energy window that corresponds to the gamma rays for potassium, one for thorium, and one for uranium. So this is a different tool. You have to request the logging companies that they run this instead of the standard tool, and separately they are going to give you the count rates converted in API units of gamma ray calibrated. Typically what happens is this: when you have the 3 count rates separately, or the 3 corresponding gamma ray logs, then you can recombine them, if you will, by doing a linear average where the weights are given by the particular tool. Sometimes when you do this recombination, we eliminate the uranium log and we call it the calculated gamma ray log, or the calculated gamma ray log. The idea is that you eliminate any possible effects coming from organic material when you constitute the gamma ray logs. Sometimes you stay only with potassium, or you stay only with thorium. So if you suspect, for instance, that the grains have abnormally high concentration of potassium, then when you reassemble the gamma ray log, you reassemble it without taking into account the potassium log, and you only pay attention to the thorium and uranium. Likewise, if you suspect that your shale or your rocks have abnormally high concentration of organic material, then what you do is you eliminate the uranium and you reconstitute the gamma ray log from its potassium and thorium parts. This happens very often when you have coal, for instance, of any type of organic material. In that way, you eliminate the bad guy, so to speak. The bad guy meaning the one that is not responding to shale. So when you eliminate it, you are left with a component of the gamma ray log that truly responds to shale composition. That's the way it is. And here is just to indicate again the different energy windows that we have for uranium, for thorium, and for potassium. So what happens is that different logging companies, like Schlumberger here, they have their wind energy windows open at different bands of the energy spectrum. And each one of these windows is going to collect gamma rays coming to them and is going to assign them separately to the count rates of thorium, uranium, or potassium. Consequently, the logging company is going to give you 4 gamma ray logs. 1 for thorium, 1 for uranium, and 1 for potassium. And the same logging tool can have either the standard gamma ray log, which is with the scintillator that takes into account the gamma rays coming from the 3 elements at the same time, or they can plot the standard gamma ray log as reconstituted from the individual counts from thorium, uranium, and potassium. That's how it works. Here's an example of page 45 of the well log compendium. What I want to show you from that compendium is that Here are the thorium, uranium, and potassium logs. And here is the standard gamma ray log. Let me enlarge this image so that you can see the units. So here on the left, we have the gamma ray log. This gamma ray log was acquired from a standard gamma ray log, that is a scintillator photo-multiplier that captures at the same time the gamma ray log, the gamma rays coming from thorium, uranium, and potassium. And it has another instrument in the same tool that separately measures the count rates coming from potassium, uranium, and thorium. Please note that the potassium log gamma ray is written in percent because that tends to be the most abundant, the one that has the highest count rates. And thorium and uranium, because they're less, in general, less abundant than potassium, they are displayed in parts per million. So we have the parts per million. What I want to point out is this: when you have rocks, sandstones, and shales in which you don't have abnormal grain compositions, that is to say that the fragments, the grains that make up the grain packs for either the sandstone and the shales, they were formed under normal conditions. The constituents did not have abundant potassium, abundant uranium, and so forth, so on. Then everything works fine, and you can see that all the three, uranium, thorium, and potassium, they correlate very well. They work as a team. Let me explain what I mean by they work as a team. One decreases and the other two decrease as well. One increases, the other two increase. So they have the same correlation. One goes down, the other two go down. One goes up, the other two go up. Maybe not in the same difference or amount, but they have this tendency to correlate linearly and their increase or decrease. That's what we see when we have normal grain constitution, and therefore standard gamma ray log that you have here, the green color one, could be used with no problem to quantify volumetric concentration of shale. All right, now here's an example, page 154 of PGE well log compendium. What I'm showing you here, which is a beautiful example of the Eagle Ford formation. This is an organic shale. So now, welcome to the organic shale world. How does it work? Very interesting. Look at this. Look at the gamma ray log here. That's the green color. Then we have the resistivity logs, which are almost overlapping all of them. And looking at the deep one is the red. And then on this track, we have the spectral gamma ray logs, separately indicated by potassium, thorium, and uranium. Now, very interestingly, if you look at the gamma ray logs here, you will say, well, at the bottom in the lower Eagle Ford formation, the gamma ray log increases substantially with respect to the upper Eagle Ford and Austin Chalk, or even the Buda formation. And why is that? And you say, well, that's a shale. But you know, if it's a traditional shale, you would expect that an increase in gamma ray will have a decrease of resistivity. But that's not the case. Look at the resistivity log. The resistivity log increases when the gamma ray log increases. That's not what we typically see in a shale. What's going on here? And the answer is, that is the presence of organic material. So in other words, not all the pore space of the shale is occupied by water. If it were occupied by water, yes, as you increase the gamma ray values, then you would expect the resistivity to decrease. But it doesn't do that. And why? Look at the spectral gamma ray logs. In fact, let me enlarge this view. What's going on here is that the uranium
component of the gamma ray log is the one that increases substantially with respect to the increase observed in the thorium and potassium logs. Look at this. And why is that? Because of the presence of organic material. In fact, in organic shales, it is very commonly the case that the presence of organic material is immediately detected by the abnormally high values of the uranium component of the spectral gamma ray logs. In fact, if you go to the upper Eagle Ford part, you are going to see that the upper Eagle Ford also has traces of organic material, and sometimes we even have that in the Austin Chalk, as you see here. Of course, they come in patches, but the most substantial presence of organic material in this example is, of course, taking place in the lower Eagle Ford formation, and that's the best place to produce hydrocarbon in this area. Of course, when we do this analysis in organic shales, it's also very important to assess the level of maturity that the hydrocarbons have, their porosity, and other geomechanical properties. All of those combined is what defines whether this shale is producible or not by enhanced means such as hydrofracturing. Another very interesting example of the application of spectral gamma ray logs. Now, and here comes the same example from the Vicksburg formation that I showed you before, which is on pages 47 to 49. The only difference is that now, in addition to showing you the gamma ray log, I'm going to show you the spectral gamma ray log. Remember that there were some places, notably here at 1800 and 1600, where we observed that the gamma ray log values were high, considerably high, but everything else indicated that this was a sandstone because of resistivity values. But now, let's look at the spectral gamma ray logs. What happens here? Here's a very interesting enlarged view of the same problem. Under normal situations, you would expect that when the gamma ray log decreases, resistivity increases because these sections are hydrocarbon saturated, and you would expect that the thorium, uranium, and potassium log will tend to do approximately the same. In other words, correlate. If one decreases, the other two decrease. But see, what happens over here in the section that is just below 1600? We see that the gamma ray log increases, but the resistivity increases. So that's counterintuitive. But then what happens here? Look at this. The potassium spectral gamma ray log decreases, but the uranium and thorium logs increase. So there's a contradiction. They do not correlate. They don't have the same increase or decrease slope with at the same time. So that contradiction is already telling us that there's an abnormal grain composition. Elsewhere, they behave fine. Another section of the log that I mentioned before that also has abnormal behavior is this below 1800. Here in large, where the gamma ray log increases, resistivity increases, but we also see that the potassium log has a tendency to decrease, slight decrease, but that decrease opposes increase of the thorium and uranium logs. So what's going on here? So it turns out that in this section, the standard gamma ray log, which is the green one here, is affected by abnormally high concentrations of thorium. And that thorium was coming here as part of some abnormal grain composition, most likely due to the presence of volcanic material. So how do I fix this problem? The answer is, instead of using the standard gamma ray log here, what we have to do is to replace it with the potassium gamma ray log that we have here. If you replace the potassium, this black dash log, if you replace the green standard gamma ray log with the potassium gamma ray log, then all of a sudden everything fits in place, because this becomes a proper sensor where the gamma ray log decreases, resistivity increases. And the one below 1800 has the same issue, because now the same behavior where the gamma ray log decreases, resistivity increases. So problem solved. I could not do this if I have the standard gamma ray log. But in this case, if I have the spectral gamma ray log, I select the one that is not affected by the abnormal grain composition, and suddenly this potassium log works perfectly well along the entire depth interval of this sequence. That's a beautiful example. Now, what else can I do with spectral gamma ray logs? In addition to everything I said, there's another important thing that you can do with them, which is the assessment of the dominant clay mineral composition. How does it work? This is how it works. For that, people in the logging companies and interpretation departments have worked with templates like this. This is called an interpretation chart. Let me explain what this is. On the x-axis, we plot the potassium spectral gamma ray log from 0 to 5%. On the y-axis, we plot the thorium log in parts per million, going from 0 to 25. Now, what does it mean? What it means is this. You take your logs at any one depth. Boom, this depth, 1600. So you read the potassium and the thorium log. You read them. You take those numbers and then you plot them in this scale. And two things are going to happen. We know that as the point gets closer and closer to the origin, that means that the volumetric concentration of shale is approximately 0. That means that your rock is shale free. That means that you have a clean rock. As your point of spectral gamma ray logs plotted here gets farther and farther away from the origin, that means that you're getting into high volumetric concentrations of clay minerals. Now, when it departs from the origin, it can depart in different directions. And the blue lines that you see here, the guides that you see here, they were constructed with different ratios of thorium over potassium, which is the slope. So different slices of this quadrant are indicated here because of different ratios of thorium over potassium: 25, 12, 3.5, 2.0, 0.6, and 0.3. What do they mean? Okay, here's what it means. So when you take your point and you plot it, as I said before, the closer you are to the origin, the cleaner the rock is. But when it gets, the concentration of potassium or thorium begins to increase, the point gets farther and farther away, which means that the volumetric concentration of shale begins to increase. But the direction that it takes is very important, because depending on the ratio of thorium for potassium, we know that the most likely mineral, clay mineral, that could be responsible for that ratio, in this example where I have the point here, is elite, for instance. If it goes this way, it could be kaolinite. If it goes this way, it could be chlorite. If it goes this other way, it's glauconite, another very interesting clay mineral. Or here you can have micas. And if the potassium becomes extremely high compared to the volume of thorium, then that means that your grains have abnormally high concentration of potassium. This is no longer clay land. In fact, these red lines that you see here, they are sort of the boundary between clay land and not clay. So whenever your point lands outside this plot, in other words, when the potassium is higher than 5 and or thorium is higher than 25, then that means that with those values are not very commonly found in clay minerals. So that's an abnormally high point, and it will indicate that you have abnormal grain compositions. Similarly, if you go here in the high thorium and low potassium values here, that means that your grains have abnormally high concentration of thorium and is no longer in clay land. So typically this is not a boundary, this is not like a boundary between the US and Mexico where you know exactly where you are if you are close to the boundary. This is more like a cloud boundary, but it's just put here as a guide indicating that if you go over the red line above or below here, or if you go outside the boundary here, that means that most likely what you have is abnormal grain composition rather than different types of clay minerals. And again, the location is what tells you what the most dominant clay mineral. Of course, if you are somewhere in an area that is clustered between, say, mormorillonite, which is also called smectite, and then illite, you have a tendency to have what is called a mixed layer clay, which is a combination of illite, smectite, and chlorite. So it's a designation that is normally given to this type of association of clay minerals. But the closer you get to one of these guides, the more likely that the main clay mineral, for instance here, will be illite, and as you get here it will be glauconite. But it doesn't mean, this boundary doesn't mean that if you leave or move away from this boundary there's zero illite, because that's not the case. It just means that as you move away, the relative presence, likelihood that the presence of illite begins to decrease, and as you get closer and closer to this, the concentration becomes higher and higher. So what we typically do here is that we take all of the sandstones and all the shales and we plot them in their points and we see where they cluster. And then we compare the points of shale and the points of sandstone, and we analyze whether they have similar clay mineral compositions or not. So let me give you a couple of examples here. Okay, first of all, let me increase the size so that we know how it works. This is just for the purpose of showing you with paired scale how the different boundaries, the red boundaries are, and also how the different ratios work, or different slices. And those are, as I said before, used for reference. So here's again the example of page 45 of PGE's well log compendium. We have seen this example before in this presentation. We have the thorium, uranium, and potassium logs. Please note that these cross plots that I just mentioned eliminate the fact that you have uranium, because uranium typically comes in soluble organic matter, is not necessarily associated with the presence of clay minerals, whereas in some of these, most of the clay minerals, they have potassium, and thorium is part of the clay structure as a side product because of absorbed or detrital material. And these boundaries, by the way, they were proposed and they were designed by folks that studied a number of clay minerals, and they came up with this designation. In clay minerals around the world, or different types of rocks with different composition, and also different types of shales with different clay mineral composition. So this is a diagram. When you have specific compositions in a given basin, of course, the idea is that you can refine the guides, the limits, and so forth, so on. But this is a very general one. Okay, so let's go back to page 45. What I'm going to do is I'm going to plot all of the points for thorium and potassium according to that cross plot, and we're going to see where the points land. And here is what happens. So here is the thorium axis, y-axis, and this is the potassium axis. This cross plot that you see here is precisely the same cross plot that we have here, just a little bit modified in color, in sizes, just so that it fits on the page. But look, the limits are 25 on the y-axis and 5% on the x-axis. And those are precisely the limits that I have here 25, and 5. The colors, all of these points that you see here, separate points, are coming from the cross plot of uranium and thorium. And the colors are based on the gamma ray log. So low values of gamma ray log, they will tend to have blue colors or pink colors. And high values of gamma ray will tend to have the yellow colors, the red colors, and the light blue colors. So here's what happens. Notice that all of the sandstones that we have, low values of gamma ray, they tend to get closer and closer to the origin. That's what we expect. Now, if they were shale-free, all of those points will be clustered closer and closer to the origin, but they're not. So now we have some indication that these sandstones are not shale-free. Now, where are the shales? The shales are all located here. In fact, when you do cross plots like this in software, you can actually, what you can do is to shade the parts that are sandstones and shales, and you can see where the points, for instance, in these light blue colors, you can see how the points are bouncing off on this cross plot, and that's how the light colors are coming to this point, and the darker colors are coming to the external point. Now, the important thing here is that it seems that, yes, as you get away from the origin, the volumetric concentration of shale is increasing. So those are the shales and these are the sandstones. But what we see is they tend to have a similar thorium over potassium ratio. You see, they are aligning along a constant thorium over potassium ratio. What is that? If they were aligned, if for instance we had the sandstones here, cluster here, and then we would have the shales over here, then that will indicate that we don't have the same clay mineral composition for the sandstones on the shales. Or another possibility is if we would see another cluster of points here, then that will tell us that some of the sandstones have a different thorium over potassium ratio and some have a different. And because of the differences of the ratio, that will tell us that the dominant clay mineral composition would be one for a set of sandstones and another one for another set of sandstones. But in this case, it's very clear that we have a common denominator. And if I go back to that diagram here, you will see that they are aligning across this. And that means that we have presence of chlorite, smectite, and kaolinite. That's what I would immediately say from this tendency here. If the tendency had gone this other way, I would say, well, they seem to have an abundance commonality of mixed layer clay, elite, and micas over here. But because they're aligning across this thorium over potassium 12 ratio or nearby, I already know that all of the sandstones and all of the shales, they have a common dominant clay mineral composition. So that's what we see here. Interesting example. This is when everything works fine. Let me show you a second example where things don't work very well. And this is example on pages 47 to 49 of PGE358's well-log compendium. As the one that goes through the Vicksburg Formation. It is the one that I showed that certain sections of this example had abnormally high values of gamma ray, and they were due because of their abnormally high thorium concentration having to do with potential volcanic events. Now let's do the cross plot. Here is what we see in the cross plot. Compare this to the previous example. Now we have different sets of clusters and we don't have a common alignment of thorium over potassium ratio. You see that? It's not common. Some points, they tend to have a different ratio or cluster of points, and some other points they tend to have a different ratio. As I indicated before, we would say that as the points get closer and closer to the origin, that would indicate that the sandstones are shale free. If you compare these values to the values of the previous example, you will see that the cluster of these green points is farther away from the origin than in the previous example, which indicates that compared to the previous example, these sandstones are a little bit shalier than the sandstones in the previous example. In fact, the colors that you see here are coded according to the gamma ray. So the gamma ray values are the lowest here. So that will be, those are the cleanest sandstones. All right. Now, what happens when you go in this direction? They tend to be the shales. You can see that this group of rocks, the ones that are enclosed in this light blue cluster, and the light blue cluster is shown here in the striping. So all of the points included in this light blue cluster, and the circle is light blue, or the enclosure light blue, they come here in light blue, and you can see that all of those are the sandstones which exhibit the typical behavior in the logs, which is low values of gamma ray log, high values of resistivity, and they correlate very nice to the low values of potassium log. So everything is working fine there. Now, but what happens is this: the abnormal locations, the abnormal situations, which are with the pink, they are all enclosed in this cluster right here. And what's going on there? What's going on there is that we have an abnormally high value of potassium. So those clusters, the points that are in these clusters, are all the ones that are highlighted here in pink. Look at this, all of this pink. So it turns out that the ones that are highlighted in pink are the ones that before we recognize as having some abnormal grain composition, because the correlation of thorium-uranium was not in agreement with the correlation with potassium, and also because at those points the gamma ray log would increase. So consequently, this diagram is telling us that all of the pink color striping points that are abnormal behavior, all of them come in a cluster that is far away from the origin, and which is indicating that we have abnormally high concentrations of thorium. So all of those sections that are pink color here they're actually sandstones, they're not shale, and the reason why the point gets all the way up here as opposed to below here is because we are in the region of abnormally high concentration of thorium in the matrix, not in the shale. So that's how we diagnose that this cluster is abnormal, whereas the other clusters, the green color that you see here, all of those are shales. And the light blue colors, all of those are normally behaved sandstones. So here is another element how to use the designation here. And also the typical orientation that we see for the thorium potassium ratio is indicating that the dominant composition is elite and mixed clay layer. That's the dominant clay mineral composition for the well-behaved sandstones and shales. Good. That's beautiful application. So in summary, we have found that it's very important to diagnose situations where the gamma ray log may or may not correlate with volumetric concentration of shale. This has to be done by understanding, honoring all the behavior of all the logs, gamma ray log, resistivity logs, and density logs, and neutron density logs. If we see something abnormal with the gamma ray log, which, for instance, super high values of gamma ray log, when we see that there's invasion and there's good porosity, then we see there's something abnormal with the grain composition that is throwing the values of the gamma ray way too high. The other thing that I found that I show you is that gamma ray logs, they need to be calibrated, quality control, and corrected for environmental effects. This is actually very important if you're working in a multi-well project, because in a multi-well project you may have wells that were drilled with one mud, with one size, and they were logged with different tools. So if you try to compare the gamma ray logs across many wells, then you're going to find that often they don't have the same values. And why don't they have the same values? Well, because they were not environmentally corrected. They were not corrected for borehole size, they were not corrected for type of mud, and maybe they were not corrected for temperature. So it's very important that all of them be corrected if you are going to be comparing logs across multiple wells. So I show you that if you have abnormal grain matrix compositions, such as in the case of potassium-rich minerals or thorium-rich minerals, presence of organic material abundant, or presence of thorium, presence of volcanic materials with abnormal compositions, then they can produce high values of gamma ray, not because you have clays, not because they're shales, but just because the grains have abnormal composition. This is not something that happens very often, by the way. If you ask me how often am I going to see something like this, well, based on my experience, I would say maybe 5% of the cases. But you have to be aware of this because this happens in some regions of the world, not only in the US, but across the world. So when that happens, the only solution to the problem is to request the logging company that they run spectral gamma ray logs so that you have a tool that produces count rates for thorium, count rates for potassium, and count rates for uranium separately. And then you analyze all those logs and you see which one is the one that is affected by abnormal grain compositions. You take it away from the mixture and you work with the ones that are not affected by abnormal grain compositions. And that one is, or those ones are the ones that you can use to assess volumetric concentration of shale. And the last thing that we saw is that spectral gamma ray logs, they can also be used to assess the dominant clay mineral composition. And I have a few review questions. Please make sure that you read them, make sure that you know how to answer them. The idea is to quality control the learning. I have two sets of questions as shown here. Please look at them. And also, I would like to acknowledge the help from Baker Hughes and Schlumberger to use some of their material that they gave me very nicely to produce this presentation. And with that said, thank you very much. I hope you enjoyed the presentation. I hope it was not too long. Please note that some of these recorded videos I go into more length because what I want to do is to give you more detail. We don't have to face-to-face way to quality control the learning, and because of that, my job is to make things a little bit easier, more slowly, more digestible, so that all the elements are properly explained. I have more examples, and I take more time to explain the different elements. This presentation, the elements of this presentation will be part of the next homework. The next homework will have cases of abnormal gamma ray logs, and also we will have spectral gamma ray logs, and the idea will be to diagnose the dominant type of clay mineral composition. With that said, thank you so much. Have fun. I hope you're having a good semester. Stay healthy, take good care of yourselves, and I also hope that your families are doing well. Thank you. When rocks are made in the rock factory, so to speak, they're not like this, but they come in very large shapes, sizes, and it takes a lot of geological time, mechanical and chemical weathering to come to something like this. Lots of organic material, lots of clay. So when rocks are made in the so-called rock factory of the earth, they do not have a whole lot of different components, but it's the mechanical, chemical weathering action over time
that causes them to become like soil. And when they do that, the particles are so small that they include silt, clay, and porosity, water in this case. But the presence of clays is not something that happens instantaneously. It requires a very long, prolonged period of weathering action before we have the standard clay minerals that we often know here, and small presence, the small components. And so if you take your gamma ray log over a large piece of rock like this, you will see that the values of gamma ray log will be relatively small. But as you go into the Earth's cycle of weathering, chemical or mechanical, we have more and more clay particles, and the particles become smaller and smaller. So if we look at the gamma ray log of the soil here, you will see that the values for the same volume of material will be considerably larger. Why so? Because in this material now we have a much larger concentration of thorium, uranium, and potassium. Potassium is a very common element of many of the clay minerals. Uranium is soluble and is present in organic material, and thorium is not soluble, but is often present as a tritle material attached to clays and other materials. So that's how the gamma ray log of clay minerals and shales is so much larger in magnitude than the gamma ray log of clean rocks.